Okay. So there's actually not much logistical things to talk about, except there are two, which is one is of course related to assignment number 5, and the next one is related to the project. So where are we? We are on this lecture. So we're actually last but one lecture. We are in the last but one lecture. So since it's towards the end of this course, the topics will get heavier. And so today's topic is hidden Markov models related to time series models that you might have seen elsewhere. But again, the objective is not to expose you to too many models at the same time. To kind of pick one prototypical model called a hidden Markov model and try to understand how it works and what is its assumptions and so on. Okay, so that's the scope for today. As you know, assignment is due in 7 days, right? So the assignment number 5 actually involves hidden Markov models that we'll cover today, but it also involves two unsupervised learning techniques. One is principal component analysis, and the second one is k-means. The objective is today we'll certainly try to cover k-means as well in the second half, and hopefully we can cover hidden Markov models in the first half. Principal component analysis, if we can cover it, we'll try, but I don't want to rush through. If not, we'll try to cover it in the next lecture. Okay. Of course, the assignment is due the same day at the end of that evening. So principal component analysis is something I've seen in 572. Some of you have seen it in 572, probably have done it. So hopefully the question is not too complicated. It's just asking you to apply a PCA and then see a clustering output, and don't apply PCA and look at a clustering output and of synthetic data that you generate. So it's not too complicated. We will maybe I'll look at the assignment questions a bit later. Okay. So that's about assignment. The next quick logistical thing is about the project. Project is due 2 weeks from now. Irrespective of when your presentation slot is, it's due 2 weeks from now, so no extension for fairness. So try to do spend time on it, because given 2 weeks and the amount of grade for a project, almost 3 times an assignment, right? It'll be good if you spend some time on it. And it's not because I want you to submit, project is open-ended, right? So we are not trying to, in contrast with assignment where you have to do exactly that, otherwise you'll kind of lose points, right? But the open-ended nature is not to help me, but to actually help you guys do something that will be useful to talk about. Whenever people ask, hey, what is your machine learning experience? You can say, hey, I worked on XYZ data set, I worked on exploring, certain attributes, I saw certain patterns, and based on that, I did some analysis, right? So hopefully that will give you something to talk about, after this course. So do try to work on it. We only were able to do one sync with the TA and myself, I guess, about a month ago. But there were no, I think all the projects of all the teams were pretty, well scoped. So I don't foresee an issue, but I'm sure in the next 2 weeks when you try to wrap up, you'll hit hurdles. Try to not be stuck somewhere for multiple hours or days. Try to go with some heuristic or some other side step if possible, if you're hitting a bottleneck. So that's about the assignment and the project. Assignment, I'm not going to open up the page because there's a lot of details there. And first session, I want to keep it for hidden Markov model. Okay. But otherwise, any questions about the logistics? Yeah. Okay. So if not, let's actually get started. So today's lecture slides are 10A and 10B. 10B is the one which is covering k-means. 10A is the one which is covering hidden Markov models. And I'll also briefly mention what we covered last time, because last time we saw Naive-based model, or in general, further discussion on generative models. Today's model is also an example of a generative model, but it kind of deviates away from the previous models that we saw, in the sense that Naive-based model and Gaussian discriminant analysis were mostly about, again, classification. Although we are learning something about the X part, the input part, which is in fact the marginal probability of X or the conditional probability of X given Y, they still were focused on like classification. So they were very similar to, you can plug and play, remove remove Gaussian discriminant analysis and plug in like a SVM or a decision tree and so on. So they, it's the input output patterns are the same. Okay? So it's basically supervised learning problem. But today you'll see that it's not a supervised learning problem. So input and output will be different. The problem itself will be different. Like what is exactly your modeling using data will be slightly different. Okay. So that's a big departure. And so if you're familiar with time series models from some other course, you might not have seen this because this is not a typical time series model. It has its own set of assumptions. But if you've not seen time series model, this is a good model to know in your toolkit. Okay, this is not probably the starting point for your time series data, but maybe a good initial model to get started with. So very similar to starting with XGBoost, for example. Similar to that, you can use hidden Markov model as an example model to start with your problem. Okay? So actually, yeah. So I will not actually. So a few slides about again generative models and then Gaussian discriminant analysis and in particular naive-Bayes modeling. I will actually skip naive-Bayes modeling related recap, except to say that last time when we covered naive-Bayes modeling, there are two versions of it. In one version, you're only looking at the existence of a word in your input example. In the second version, you're looking at the counts of that word. Okay, so one was the the Bernoulli naive-Bayes model, and the second one was the multinomial naive-Bayes model, and they have slightly different estimates. Okay, so of the parameters. But the core idea being that there was some parameter exclusion if you did not make a particular assumption which is actually a conditional independence of solution. So conditional independence, as it says here, I guess here this slide is about parameter counting, so we're not going to look at that. But conditional independence assumption is kind of key. Conditional on the class, the probability of any given word is independent of any other word. Okay? So without the conditioning, it's not correct to say that probability of any given word is independent of the other word. The conditioning is important. Okay, so that's the key assumption. And then we saw two versions, Bernoulli and multinomial. And there's some parameter counts here, but basically what happens is instead of exponential in the number of words here or number of categorical features, you have something which is linear in the number of categorical features. You still have a lot of parameters, right? Instead of looking at 3 parameters or 10 parameters, you have 100,000 parameters here, which is a lot, right? Even for this simple model. So, but at least it's a step up from this version where you had an exponent which you could not really model. Okay. I will not look at the parameter estimates. It's basically counting and normalizing. I will skip those two recap slides. And so this was the slide where we ended last time. Okay. So again, those who just came in, we're not talking about. Right. We are gonna so where we are. Last lecture we talked about generative models. We looked at parameter estimation and constrained optimization actually, and then we saw Gaussian discriminant analysis last time, and then we saw both the Bernoulli and the multinomial versions of the naive-Bayes model. Okay. So today, we'll do a quick warm up of. It's not really a warm up; it's a recap of naive-Bayes, but a fix to the naive-Bayes, which is also part of your assignment number 5, which is called Laplace smoothing. Okay, it's a very simple idea. I'll briefly mention that, and then we'll go over and talk about a hidden Markov model. Okay, so all these models, by the way, are generative models. So the list in this list, there are 3 models. The last 3 bullet points: Gaussian discriminant analysis, naive-Bayes, and hidden Markov models. All 3 are examples of generative models. Okay, the first 2, of course, are kind of related to supervised learning. The last one is not exactly supervised learning, so we're going to discuss that today. Okay, so with that, let me talk about Laplace smoothing. Yeah. So what is the concern? The concern is that there may be a word that the train, it's part of the vocabulary, but the training data never saw it. So it was part of the vocabulary. Let's say you pick up the English dictionary and say, hey, all these words are part of my vocabulary, but your training data is small enough that not all words appear there in any one of these emails, for example. In particular, informs is just a random word. Don't think of informs as any specific relation here. It's just a word. It's just that let's say you're training emails for the spam classification prototypical example that we've been talking about. We didn't have this word, but it's a part of a vocabulary. Then what is our naive-Bayes classifier prediction? If the word doesn't exist in training data, our prediction, remember, our prediction involves predicting, a class, but to predict, there's some parameters that we're estimating. There's one parameter per word given class. Okay, for example. Okay? So if there's a word like informs, then it's a word in your vocabulary, then there's going to be a parameter corresponding to that. And there's going to be a parameter for both the spam class and the non-spam class. But what will our estimate be? It will be 0 because the word was not there in training data. Okay? So although there's a lot of messy expression here, I mean, this should be, we have seen this expression from the k nearest neighbor time from some time ago, but basically it's a count of number of times the word appears in the positive class divided by the number of examples of positive class. That's 0 because the word never appeared, and similarly the word never appeared in the negative class as well, so it's 0 because the word never appeared in a training data. So this estimate seems to lopsided, okay? Because then what happens is if you have this estimate for the word 575th word, then what happens is when you make a prediction, remember when you're making a prediction for a class given an input, in that input if the word is present, then there is an issue because one of the parameters is exactly this. The p of 575 given y is equal to 1 is exactly one of these terms. It's a product of these, product of such terms. One of the terms is 0. Then the numerator will be 0. Yeah, similarly, denominator is just a very similar thing, same term and the opposite class. So both numerator and denominator will evaluate to 0. Okay, in this prediction for class is equal to 1, and similarly prediction for class is equal to 0 will also be 0 by 0. So it leads to some edge cases, right? Errors. So instead of that, what you can do is not try to set 0 for things that you've not observed in your training data. Okay, so parameters, you're basically just lifting them away from 0. That's what we want to do as a heuristic. So some event or some word is not observed in the training data, then whether to estimate the probability of that word or that categorical value to be 0 or not, it's probably not a good idea. So a way to fix it is to do some sort of what is called smoothing, but the word informally just means we want to kind of lift the numbers away from 0 because we expect, since it's part of vocabulary, we expect that word to be there somewhere. Okay? So what do we do? Let's talk about the Bernoulli Navy-based version, and then I'll briefly mention it's going to be similar for the multinomial Navy-based version as well. So the fix is a very simple fix. You just add an offset to the numerator and add a different offset to the denominator. Okay. So it's offset of 1 and an offset of 2 for the Bernoulli version of the Navy-based model. So why exactly this? Why not some other numbers? You can certainly do other numbers as well. There's no hard and fast that you have to do 1 and 2 here, but basically you're just lifting it away from 0. So even if the word doesn't appear in training data, your solution will be like 1 by the number of positive classes plus 2, for example. Okay. So you're basically avoiding 0. And why the 2 and 1 are related in the sense that if you're adding 1 here, the 2 is because there are 2 potential outcomes. The 2 potential outcomes for the word. So this 2 is just counting. Sorry, there are 2 potential classes that are possible. So this 2 is just counting the number of classes. Okay. It's just a particular choice because of which what you can do is then evaluate, hey, does the conditional probability of my word sum over j is equal to 1 to n evaluate to 1 or not? Okay, so this choice of 1 and 2 are such that this is the probability for word j under class y is equal to 1. So sum over all the n words that can happen, sum over all the probabilities, because under class 1 you basically have a probability mass function over each word. Okay, so they should sum up to 1. Right? So probability mass function over each word in my vocabulary. So it's 1, some positive mass for each word. So they should sum up to 1. And so this choice, lets you, ensures that it sums up to 1. And similarly for the other one, it's the same fix, and so it also sums up to 1. This is just for consistency. Otherwise, if you arbitrarily change probabilities, then you may not have you may have the issue of summations not summing up to 1 basically, which is the basic equality that needs to be satisfied for probability mass function. Okay. we don't have to smooth P of y. So remember, P of a word given positive class, P of word given negative class, we are smoothing like this. Those are two sets of parameters for the Bernoulli Navy-based model. There's also one other parameter, which is the probability of a positive class, for example. Okay, or probability of negative class is where they sum to 1 here. So we don't have to smooth P of y. That's because you need to have two classes. In the sense, you need to have at least one observation which is spam and at least one observation which is non-spam. So you don't run into the 0 by 0 error. Okay, the number of positives divided by the number of observations is at least going to be greater than 0 for sure, because you need to have one of these classes. Otherwise, you can't classify if you don't know the second class. Okay. Does it make sense? Like what I suggested here is just an offset you're providing so that you avoid the 0 error. Okay. Any questions? Okay. Okay. So what do you do with the multinomial Naive-based version? So if you want to kind of be analogous to the Bernoulli version, then you just need to pick the number of okay, sorry. So the number of the denominator to be the size of the vocabulary. I think in the previous slide, sorry, I said the number of classes. It's not really number of classes. It's just the intuition is just that the word is present or not. There are two events that can happen, and so it's just a count of events. Here, it's the vocabulary size. It turns out that it's because here the counting is different. It's counts times counts for each word times the number of times it's present, number of times you are in the positive class, instead of whether the word is present in the positive class in the examples which correspond to the positive class. Okay, so slightly different counting and normalizing here, and that's why you have a slightly different offset. Again, the offset, you can easily see that if the first term is 0, then you still have a 1 by some positive term in the denominator. Okay, so again, here you basically are increasing it by the size of the vocabulary because the count by count is different parameters here, different I guess ratios here. Again, you can check for this choice 1 by v. The sum is again is sum to 1. Yeah. Any questions here? So nothing changed. We just lifted the probability such that they're away from 0. That's Laplace smoothing. Yeah. So last couple of comments on Naive's. Naive's assumption is somewhat strong. It's saying conditional on the class, each word is independent of the other. That is kind of strong. I know it really factorizes and reduces our number of parameters, but at the same time, it is a strong assumption because the conditional independence may not be true. Okay, they may not be independent. Okay, even a condition on the class, the occurrence of a word and the occurrence of another word may not be independent. For example, maybe there's a dollar sign, and there's a some other currency, euro. Then conditional on some class, the probability of a dollar occurring and the probability of euro occurring may be related to each other. If it's dollar, then maybe it's not going to be euro, for example, right? But here we just say, hey, probability of dollar occurring is nothing to do with probability of euro symbol occurring, for example. Yeah. So Naive-based is an example of a generative model, just like Gaussian discriminant analysis. And so kind of that gives us a pattern for setting up a hidden Markov model. And the pattern is Naive-based is an example of probabilistic model. Okay? Probabilistic, I guess, graphical model is the missing piece here, but basically a generative model. A generative model and probabilistic model, maybe informally you can exchange the words. So what we do is that we kind of describe everything as a random variable. Okay? So in particular, for example, x's and y's in our previous case were random variables. Okay, x was a random variable, y was a random variable, and y is a random variable. We have seen it before because even for generative discriminative models, y had to be a random variable so that we can talk about, like if you remember, linear regression, y was a normally distributed random variable with some mean theta transpose x plus some noise, okay, epsilon noise, right? So you somehow define random variables of the quantities of interest. If its classification is going to be generally x and y, then you say, hey, how are x's related to y's, or how are x's related to each other? Okay, so that's the second point, like make some assumptions about, hey, some things may be independent of each other. Okay, so I mean, of course, naive seems to be the only, a natural way now that we've seen it, which is condition on the class. Each random variable, is, for example, first word being present or not is independent of the other. That's one example, but there could be other specific independences and conditional independence assumptions that you can make. Okay, so why make these assumptions? They just generally what they do is help you reduce the model parameters. Okay, if you don't make these assumptions, when you define the model, once you have a bunch of random variables, there's always going to be a joint distribution between them. Okay, if there are 10 random variables, there's going to be a 10 huge joint distribution between them. That can kind of you can reduce the number of parameters to describe the joint distribution. So think of a discrete distribution, right? So each random variable taking two values. If you have a joint distribution without further assumptions, you will have to have a huge table of 2 to the power, 10 to the power, 2 to the power 10 rows, and then for each one, what is the probability of the collection of random variables taking certain value. So I think you might have seen these probability tables or conditional probability tables before. It's just that these assumptions will kind of help you reducing that table essentially, and that's what we did for name base. And then once we have set up the model, parts 1 and 2, then we generally want to either estimate the parameters of the model, or okay, here we don't talk about the second part, but let's say we just focus on estimating the parameters of the model. Okay. Sometimes the estimation part of estimating parameters of the models is also called inference. Although more, I guess, correctly, inference means inference of conditional probabilities, expectations, and so on. So if the model parameters themselves happen to be random variables, you can talk about inference. But okay, loosely speaking, training the model given the data is just about estimating parameters. Okay, so basically this part is where you will think of something like maximal likelihood estimation. Okay, or with constraints and things like that we saw earlier. There are other techniques that we have not seen here. One of them is called expectation maximization. Okay, EM. We might see EM later if we have time, but EM is another technique to train the model parameters given the data. Okay. So any questions? So this is a very general template saying, hey, if you have generative modeling perspective, then how do you, or a Bayesian modeling perspective? So Bayesian models are also very similar to generative models in some sense. You need to first you start with a model definition of what are the random variables, how are they related to each other, some of them independent of the other, maybe conditionally independent of the other, and then you kind of figure out an estimation technique. Generally, maximal likelihood estimation may not work, and so you have to go with some more exotic approaches. Okay. And then, of course, use the model, which is mostly prediction given a new input. What's the likely outcome? Conditional probability of y given x, basically. Or you can sample also from this distribution, conditional distribution. Okay. Any questions about this template? Because then we'll get into a specific version of this, which is for hidden Markov modeling. Okay, so this is actually a big departure from almost all the previous models that we've seen before. We are not going to be talking about supervised learning. Okay, so really, whatever you're thinking about supervised learning, put it aside for now. So there are different types of data, right? So here we're just trying to show that there is a data set which could be temporal in nature, time index, right? And a priori, if I don't tell you anything, you can always, make versions of this derived data which can be a supervised learning problem. But here we really don't want to do that way. So we're not going to go to the supervised learning path. We just want to say, hey, there's some polar structure in the market data. Let's say this is some particular stock price. How do we represent it using appropriate random variables, and then learn the parameters of the distribution governing those random variables, so that we can do something similar to supervised learning, but also maybe other tasks. And those other tasks are enabled only because there's going to be a generative model. In particular, for example, here, given this observed sequence of words, there is a part of speech tag that you can attach to the collection of words. Okay, this part of speech tag. Okay, so there is a so first of all, there's an order relationship between these words, right? Because if you mix them up, then it's not a sentence. But also, these tags are extra information that kind of go along with these observed words. Okay. So what I want to illustrate from the previous slide is, although I showed the stock market example before, that was just temporal structure. The previous slide was talking about, hey, here's this collection of words or a sentence basically, and there is part of speech value associated with each word. So what I'm trying to motivate towards is the notion of that there could be things that we observe and there could be things which we don't observe, okay, a priori. For example, observed would be these three, I guess, notes. I'm just calling them notes, but basically these three words, I feel happy, that's observed, okay. But behind the scenes, there could be a bunch of random variables that are getting realized, okay, or bunch of random variables that are taking specific values. For example, the first random variable taking a value pronoun, the second random variable taking a value a positive verb and positive adjective and so on. Okay. So what I'm saying is observed states or observed states just means, don't worry about it. It's just a observed state means observed feature or observed observation. Okay, so that's I feel happy. Behind the scenes, there could be unobserved features. So think of a missing column in your data. Okay, so for example, even the time series one or in the sequence of words case, there's a missing column so if there's a column, there's a random variable associated with it. It's just that columns, the random variables values are kind of, you don't have it in raw data, but you assume that there is that column, and that column, that random variable is taking some value. So what are these arrows and so on? We'll talk about a little bit later. Okay. So all I'm trying to motivate here is that there could be some observed sequence of observations. There could be a sequence of random variables, realizations of random variables. Okay. So she is a realization from the vocabulary, cells is a realization from vocabulary, and so on. Similarly, these other guys, other realized values are also observations from some random variable. Okay. Or one more random variable. Okay, so here is a more complex example. So let me actually skip this one because I have to explain more than it's needed. So let me skip the audio signal processing example. So again, just coming back to just temporal structure, there is a temporal structure even in biology, right? So the data sequence. So anyway, so what I want to show is that sequential data, with temporal structure, basically include time series analysis, like market forecasting, the curves that we saw earlier, weather, sensors, other temporal data. Natural language processing, very good candidate for sequential analysis, sequential modeling, part of speech tagging, speech recognition, the slide that we just skipped, and other things like sentiment analysis. And biology includes DNA sequencing and gene prediction and so on. And there's also engineering applications to sequence data, okay, sensor data, which could be sequential in nature. Okay, so all these types of situations or application domains, right, where you want to work with sequential data. It doesn't exactly look like a supervised learning problem a priori. You can always create some supervised learning problems, certainly. Is where you have this data, you can always build a model like a HMM model. Okay? And it has its own assumptions. First of all, you can see whether the model matches to the data properly and whether that is the right model for you to pick and learn and use for some downstream questions that you have. Okay? So there are all those aspects that we'll cover. Okay, so we'll cover starting now. So when to use hidden Markov model. So we're gonna talk about what's hidden, what's Markov, in this model soon. But hidden Markov models, let's start with where are they suitable. They're suitable when you have a sequence of observations. Okay? Sequence of observations is just exactly key cells and so on, right? That could be one sequence, or it could be just some number sequences or categorical sequence, whatever it is. And each observation is a you want to assume that it's a random result, probabilistic result of a corresponding hidden state of a dynamic system. Okay, so that's where I was showing the text example. So there is some hidden state. Okay, there is some hidden state that's realizing from where you're getting an observation. Hey, now I want a pronoun. Let me sample a pronoun. It just happens to be I. Let me sample a positive verb, and it happens to be feel. Let me sample a positive adjective. It happens to be happy. Okay, this is not exactly hidden Markov model, but I just want to show that there is a where this hidden Markov model makes sense is that you have a sequence, and then you want to kind of hypothesize that each observation is a stochastic output from a stochastic output that corresponds to a hidden state or a hidden feature value that I don't see. Okay. Hidden means just I don't see of a dynamic system, in the sense that what I don't see itself, has some temporal dependency. Okay. So, and of course, this state or whatever, the thing I don't see is unknown. Of course, in my data, there is nothing like that. So in my data is just a sequence of observations that I'm seeing. So, okay, let's actually. So this slide is not useful. So let me skip that. So, so here is an important slide which kind of sets the model. So we have a setting where there's a discrete time index. Okay, t is equal to 1 to 2 to 3 and so on. At each time, the system, the system as in like whatever you wanna, like whatever setting you have, application domain, there is some random variable. Okay, there is some random variable that's taking a specific value st. Okay, so capital letters are for random variables and little values are for realization. So at each time, there's the system or whatever the application is in a certain state, okay, hidden state, a little st. Okay, so I'm indexing by t because this is the time at which I'm saying the state of the system is little st. So there's a corresponding random variable whose realization is little st. Okay, and then we can also assume that there's the starting state is, so what would be the starting state? It's just some distribution from which I sample. Okay, so there's an initial distribution from which I can get a starting state. And the state, there's going to be each of these hidden states produces an observation. Okay, emits or produces an observation. So that's the actual value, realized value is little ot, but in general, there's that realization is from a corresponds to a random variable. So that random variable is capital ot based on that system state. Okay, and then so basically, what is system doing? It's assuming some state value. At each state value, it's emitting a observation, little ot, okay, based on the current state, and then it's shifting or transferring to a new state, okay, which is capital st plus 1. Okay. So the new state could be some s prime or something, but there's going to be some transition. Okay. So this textual description can be succinctly represented using this diagram below. Similar diagrams also can be drawn for naive-based models as well as the Gaussian discriminant analysis situation. But so what is the diagram here? The diagram has a bunch of nodes. Nodes correspond to random variables. Okay. So there's a starting random variable. Okay. This random variable taking a specific value is the initial state value of the system. Then at that starting state, the system produces an observation, okay, like a word, which is O1 here. Here we are only seeing random variables, not the realizations, but O1. And then the system changes its value to another state value, S2. At that state, it produces another observation. And then again, the system changes to some other state and so on. Okay, so this is just showing the t time steps. It could be more time steps, it could be less time steps, but there are capital T time steps. Each time step there is a state value getting realized, and from that a observation getting realized. Okay. And the observation, as the word says here, is what we see. Okay, so it could be a sequence of numbers, or it could be a sequence of words, it could be a sequence of whatever. But what we don't see is this hidden random variable realization, whether number or token or whatever it is, vector, we don't see. Okay. So the temporal dependence is actually completely hidden. Of course, there is these observations, if you see, they're not like directly linking to each other. Okay. If you link them, then it's going to be a different model. This is a version of hidden Markov model that's typically taught in textbooks or in introductory examples. Doesn't mean that you want to model it exactly this way. You can always add arrows whichever way you think makes sense. It's just that for them, the inference procedures or learning procedures will be slightly different. But that should not hesitate you from, like, in case there's an assumption that, hey, the system state itself, next state depends on the previous state, but also observations also depend not just on the current state, but also previous observation, you can add it. Okay, it's going to be a slightly different model. Okay. Any questions about this setting? Okay, so now let's, so the hidden Markov model, the name comes from, there's a hidden state which actually driving the dynamics of the system. As in, for example, with the stock market system, there is something behind the scenes which we're not observing. That's what's driving the numbers that we see, return numbers or price numbers that we see every day, for example. The Markov assumption is exactly, to be said, the Markov assumption is actually already captured in this, again, this graph here. So this is a graph with a bunch of nodes, the random variables, right? So this actually is called a probabilistic, so this is actually called a graphical model because the hidden Markov model is called a graphical model because it has a graph corresponding to it. And the graph actually already tells you, at least mechanically or sometimes even visually, you can see what conditional independences it encodes. Okay. Remember for naive Bayes, there was the conditional independence assumptions you're making. So here there is an independent structure we are gonna further also assume, which is the Markov assumption. Okay. The structure is in the graph. So what is the structure? You can see that if you think of some sort of flow from each node to each of these nodes, you can see that if I kind of condition on one of these random variables, the graph kind of splits away, right? So there's independence from, the preceding state, for example, ignore the observations for now. The preceding states and the next state, if I tell you what the current value is, have nothing to do with each other. Okay? That's the Markovian assumption in the sense that given the specific value that ST is taking, ST is taking some value, state value, maybe 10 or 5 or whatever. Given that the previous random variable and the next random variable, if you have not observed them, they are going to be independent. Okay, so this is actually a conditional independence assumption. Okay, condition in the current state, present state, the future is independent of the past. I guess that's the informal way to say it. But basically, it's a relationship between random variables. Okay, that's encoded here in this diagram. Okay. Any questions here? So this is exactly this is called a Markovian assumption. Okay. Okay, so this is with respect to states which we don't observe. What does it say about observations and states? Okay, so for example, if you take ST minus 1 and OT, the question is ST minus 1 and OT conditionally independent of each other given ST takes some value? The answer is, since this looks very similar to this diagram, like one forward arrow and one forward arrow, one forward arrow and one forward arrow. It turns out it is the case. Okay. So ST minus 1 is conditional independent of OT given ST. Okay. What about ST minus 1 and OT? Right. So ST minus 1 and OT without the conditioning. Okay. Without the conditioning, you can see that there is a way for them to be influenced by each other. Okay. I'm doing all this informally for at least for this slide because there's actually a mechanical way to figure out what conditional independences exist in a graph. Okay. I don't know if I don't recollect the name of the package in Python, for example, but you can maybe I can mention it offline. But there's a way to mechanically figure out conditional independence. It's not always the case that you can just looking at the graph can tell what is conditional independence of the other. But in this case, it's since it's a simple enough structure, we basically are trying to hone in on the Markov assumption. Basically, that random variables can be kind of independent of each other if I give you some value. If I don't give you that value, of course, they're not independent. Okay, so for example, ST minus 1 and OT are not independent because there's a nice connection between them. You can't just separate them out. Okay, so think of a graph where there are two nodes and there's no edges between them. That there you will say, hey, they are independent. Okay, for example. Okay, so yeah, so let's now further formalize a little bit of notation. So we say, so hidden Markov models, define a hidden Markov model. There's a few things you want to say. What are the state values? Okay. What are the observations? So state values, there's going to be a finite set of state values, and there's going to be a finite number of observation values for our treatment. These finiteness stuff we can kind of change it, okay, and that will be a slightly different model. But for now, let's assume that it's finite states and finite observations, and number of states is n, and number of observations is m. Okay. And to completely describe the hidden Markov model, there are three things we need to specify. the first thing is what is the distribution of the starting state. Okay, so the starting state S1, you know, does my system always start in the same state? Okay, so maybe state number 3. Then the starting distribution is not it's going to be degenerate distribution, with like 3 having a probability mass of 1 and everything else probability mass of 0. Right? So all I'm saying is you need to say something about the starting distribution, okay, which is just a distribution of a state, like a PMF over state because they're finite in number. Next, the second thing you want to mention to describe a hidden Markov model is the transition probability. Okay, what is the probability of the next state taking a specific value S prime given the previous state took a specific value S? Okay, this is the conditional probability. Okay, this is enough exactly because of the Markovian assumption. Similarly, in each state, you said, hey, observations are emitted values only depend on the state that the system is in. So you just have to say another conditional probability, which is given the current state value being little less, what's the probability that the observed thing is little low? Okay. So some conditional probability, again, a probability mass function. Okay. So given these three, and of course, to define these three, you need to know how many states are there, how many observations are there, observation values can be there. So given this is a complete description of a hidden Markov model. Okay, at least this version. They can be changed by changing a lot of things. So one thing you to observe here is already that this probability of st plus 1, taking value s prime, given st takes a value is less, it doesn't depend on t. Okay. So you could have said probability of s2 given s2 taking value s prime given s1 taking value is less is the same as probability of s10 taking a value s prime given s9 is equal to less. Okay. So it doesn't depend on time. And that's why it's called a homogeneous hidden Markov model. These transition probabilities don't depend on time. Similarly, these emission probabilities don't depend on time. Okay. So if they start depending on time, that's a slightly different model. Okay. And although I'm trying to allude to the tangents of all sorts of modeling relaxations and things like that you can do, we want to focus only on this version of the model. Okay. Because once you kind of play around with this model, the other models are going to be relatively less hard compared to directly jumping into those models. Will be a little bit hard, right? So it's a homogeneous hidden Markov model. Okay, so instead of saying what the states themselves or the observations themselves could be, for example, words, right? In the part of speech tagging example, the observations themselves were words from the vocabulary. She says something, right? Instead of that, for simplicity for us, I will just say, hey, the states are actually 1, 2, 3, 4. It's like tokenization or indexing these words. Okay? So I don't know if you can always create an index for a word, right? Instead of representing the word itself. So let's say the states are 1, 2, 3 to n, and let's say the observations are themselves are also 1, 2, 3, 4 to little m. Okay. Then okay, so these are the states. These are the observations, all the possible observations. And instead of talking about instead of always using p, let's use some simpler notation. So pi is an example for a probability mass function. Okay, or the initial, it's just a probability mass function that such that pi 1 plus pi 2 plus pi 3 plus pi n is equal to 1. It's just an initial distribution over the starting, initial distribution of the state values. T is a transition probability matrix, so it's an n cross n matrix. Okay, why is it a matrix? It's a matrix where each row corresponds to what the current state value is, and then each column corresponds to what is the possible next state you can go to, and each entry there, it just says, hey, this is the probability which you'll go to the next value. Okay. So each row is basically a probability mass function, okay, which sums to 1. So row sum should be equal to 1 because it's just a PMF. Similarly, probability of an observation given state is going to be an n cross m matrix where n is when the rows are each state value that is possible. Then for each state value, what is the probability mass function over the observation? Okay, there are m values that you can take, so you have the sum to 1. So that's the n cross m matrix. Just trying to keep you guys, give you guys a different perspective instead of a previous slide where we had the conditional probability explicitly written. Here, we're just saying, hey, you can have pi, t, and q as the parameters of this model. Yeah, so you can make O not finite. I think, for example, in the previous slide, we said homogeneous hidden Markov model. You can drop the homogeneity. You can drop finiteness. For example, the observations need not be a matrix anymore. It could be, per state, it could be a Gaussian distribution, for example, with that state being, for example, the mean. S itself need not be finite, then the model is called Kalman filtering. Okay, so it's a different model. It's mostly encountered in engineering or signal processing applications, but if the state is not finite, then it's called Kalman filtering. With Kalman filtering will be the closest analog to hidden Markov. Okay, so with that notation, if you come back to the few examples that we saw earlier, so for example, DNA sequence, the observations will be A, C, T, and G, and states would be, hey, and this is a gene, this is a transcription factor or something, this part of the DNA is useless, and so on. So that's hidden. You don't see that. You only see the ACTG based sequence. Okay, but there will be this region actually of the DNA corresponds to a gene which which has to do some activity and so on, right? Similarly, NLP observations will be worse, and states could be which are hidden could be parts of speech. That was the example before, but it could be other things like sentiment, topics, and so on. Similarly, robots would be like the set of O's are all things which are observed. Okay, the actual data. S's are things that we are assuming are part of the problem, but we don't observe, and so we can, although we don't observe, we're gonna hypothesize what those values could be, and the model kind of is taking care of that. Even though it's not observed, we're gonna say, hey, what is the likely value of the hidden state if this is what we observed and things like that. If a particular observation is what you observed, and so on. Okay. Any questions here of how the HMM maps to applications? Okay. So this slide will be important in the sense that after this slide, we're mostly looking at solutions. And so that will be getting into a little bit of weeds. You can always come back to here and say, hey, what are the typical questions that we want to answer given the model, or if we're not given the model, how do we learn it? Okay. So and this collection of questions, these three questions here, for example, are very different from the supervised learning question, right? So if you had a supervised learning model, whether it's naive-Bayes or whether it's SVM or something else, you already said, hey, x's and y's are related to each other. I just tell me a function or fit a function parameters that the function kind of predicts y as good as possible, right? So here it's a completely different perspective. Here we're not talking about supervised learning, right? Here we're saying, hey, you have this bunch of observations, which is the only thing you observe. Let's say I'm looking at one particular observation sequence, O1 to OT. I'm asking, hey, how likely is the sequence? That's it. So how likely is this sequence of observations? Remember, O's are all random variables. I observed a particular little O1, little OT, and so on. I'm just asking, hey, in the model, you had all these conditional probabilities and stuff like that. Can you tell me what is the probability of this sequence? Okay. Remember, the model is actually telling you the joint probability of all the random variables involved. So remember, the random variables are O1, O2, O3, O2T, and then S1 to ST. Okay, those are the random variables, and there were some arrows between them. Okay. So in general, there's going to be a joint distribution between all of these random variables. Okay. But because of Markovian assumption, you only need the transition, like these number of parameters to talk about the joint distribution. Okay, just the pi, t, and q talk about the joint distribution. Okay, but since there is a joint distribution, you can always ask what is the marginal distribution of the observed data. Okay, so marginalize out all the unobserved or hidden random variables taking different values. Okay, that's the first question. This is an inference question. Okay, so it's a typical inference question because you have a joint distribution. Can you infer the marginal distribution? Can you infer the conditional probability? Can you infer the expectation? Okay. The second question is the second question is called is basically what is the distribution of the current state given the observation so far? Okay, so given the observations that I've observed, little O1 to little OT, what is this current hidden state? Okay, so because remember, hidden state is never observed. You observed like a bunch of words. Then given this collection of words, what is the current hidden state? Okay. You can always ask a more expanded version of this problem, which is the next version, which is given the observations that you observed so far, O1 to OT, what is the full collection of hidden states what is the most likely collection of hidden states? Okay. So remember, there's an extra argmax here. This is not exactly the full version, because in the previous version, I just want to evaluate what is the probability for any given the current observations, this observation sequence, what is the probability of the hidden state being little less, some other values, maybe the 10 values, little n number of values. If I take the argmax of them, that will tell me what the likely hidden state is for the current state. But here we are asking for what is the likely sequence of states, given that I observed these things. Okay. So this is a third type of question. Okay. So there are three different types of questions. The last aspect is learning. Okay. Learning, which is that given a collection of sequences, like think of sentences, for example. What is the model parameters? So of course you need to say what is the number of states and what is the number of observations, and then you say, hey, there are three sets of parameters: the pi, t, and q. How do I learn them given the observation sequences? Okay. So towards the end, I'll briefly mention that, but this learning problem itself is super complicated. Okay, it's called in the literature there's a word called Baum-Welch. I don't know if some of you have heard of this word or this phrase. The Baum-Welch algorithm is a special version of what is called an expectation maximization technique, okay, EM technique, which is used to learn these parameters. Okay. And why is the learning complicated? Is because you're only observing the observed state, not the hidden state. Okay. If you observe the hidden state, then the learning problem is easy. You can just use maximum likelihood, and you'll see that it's easy to count and normalize, very similar to Naive and so on. But it's not the case. Okay. So that's Baum-Welch algorithm or a EM algorithm. We'll not talk about it today or even in this course, but we'll try to kind of briefly mention about these today, because these problems, it turns out there's a specific new technique that's new to us that we'll briefly mention, which is dynamic programming, as a way to estimate these, as a way to infer these conditional probabilities or marginal probabilities and so on. Okay, so let's start with the first question, right? So what is the probability of a particular observed sequence? Okay. So to do that, as I said, if you have the parameters already, so this is not learning anymore. We're just trying to infer. Okay, so here we already have pi, q, and t, right? So we just want to say, hey, given this graph, I already tell you what the emission probabilities are, what the transition probabilities are, and all that. Can you tell me what's the probability of a particular observed sequence? Okay, O1 to OT. Then, okay, we can start with, okay, so this marginal probability, marginal because I'm only looking at these random variables and ignoring or kind of marginalizing or removing these other random variables. It's just going to be, hey, take the joint distribution between all the random variables involved and then average out the random variables that I don't care about. Okay? This is a process of marginalization, right? And the reason why we write it this way is because once you look at this joint distribution, you know that because of this graph structure or because of our Markovian assumption, we can now start decomposing this joint distribution. So what is the decomposition? We start with some starting state, S1. Then you say, hey, given S1, the next state, so the joint distribution between S1 to S capital T gets gets factorized this way. Okay. So this is exactly the Markovian assumption, where you start with P of S1 and then P of S2 given S1 times P of S3 given S2 and so on. Okay. There's no joint distribution. It's just a bunch of products. Okay. Very similar to Naive idea, where Naive is completely independent. Here it's conditional probability. Okay. Then for each state, observed random variable can be written this way. Okay. So you should check offline that this joint distribution can be factorized into these products here. Okay. Then what we observe is that actually, if you look at this summation of a bunch of product terms, what you can do is take the summation of keep the summation, for example, the last term out, okay, because one of the terms will involve OT and ST, so that last term is relevant here. But the rest of the summation terms can be pushed inside. Okay, and once you push it inside, the remaining terms, this collection here, which looks again a sum of a bunch of terms times product of terms and another product of terms, this resembles the original sum of products of products, product times product. Okay. So it resembles except for a shift of index. Okay. So this is basically called recurrence, and that's the pattern that you want to detect. So once you have recurrence type of a pattern that it detects, you can use a optimization technique or a computer programming technique called dynamic programming. It's just it's not really a programming language or anything. It's an approach to solve for whatever the original problem. If you can translate the original problem into solving for certain subproblems. Okay? So it's like recursion. For example, when you do factorial of n and factorial of n minus 1 are related to each other, right? So there's a recursive relationship between them. Similarly, here there's a recursive relationship between solving for t minus 1 steps and then solving for t steps. Okay, so finding the joint probability of O1 to OT involves finding the joint probability of O1 to OT minus 1 and so on. So that's called dynamic programming. We are not going to define it. You can look at the Wikipedia page if you want. But all it suffices to say is that it's a way to account for similarities in solving subproblems in the original problem. So okay, so if you did not know dynamic programming, what will you do? You just compute this summation for every possible value of state. Okay, so for example, think of each state taking 2 values. If there are 10 states, then there will be 2 to the power 10 rows, and each row you can evaluate this product basically, right? So that will be a lot of products that are getting evaluated, and then you would average them out, right? So that would be exhaustive computation. That's actually blowing up exponentially as the number of states increases, for example, or the time length increases, or the number of state values increases. Instead of that, this dynamic programming idea lets you compute in something like polynomial in the number of states or polynomial in the number of time steps. Okay, so we'll see a couple of examples of doing dynamic programming. We'll change the problem to not computing the first question, which is evaluating the marginal property, because that's just this, and this is very simple recursion here. What we'll do is focus on the second question, which is the distribution of the current state given the observation. Yeah, so that problem is called filtering. And if you want to look up Wikipedia for hidden Markov models, this part is doing the inference for this using dynamic programming is achieved by something called the forward algorithm. Okay. The last question here, which is find the most likely state given these observations that are observed. That problem can be solved using what is called, there's a specific name given to this called Viterbi algorithm. Okay, but again, that also uses the idea of dynamic programming. Okay, dynamic programming for us, in our context, is just, hey, when I'm doing some summation or product, just rely on previously computed summations of products. Okay, that's all for our context. It can slightly change for other settings, but we are not generalizing here. For our situation, all these 3 questions can be answered using dynamic programming. Yeah, so let's start with first version, which is trying to answer the second question there. So let's define alpha t of S to be the joint distribution of O1 to OT, little t. So alpha t means O1 to OT only, specific values that they're taken, the probability of the specific values that they're taken, and the ST taking value specific value S. Okay. So let's define alpha t of S as some, this connection, this probability, okay, this joint probability of some specific values being taken. Okay. It turns out that alpha t of S, and we'll not, so actually, looks like a, because this is a lecture version of the since it's a lecture version, I'm not going to evaluate every single equation here. It's not really useful good use of time. So what I want to show is that this alpha t of S can be related to alpha t minus of S, okay? Alpha t minus 1 of S. Okay. So I want you to ignore these bunch of equations. We can talk about them, but they're not very illuminating. But at the end of the day, what we're trying to identify is a recursion. Okay. What is the recursion? Hey, if I want to know the probability of observations little o1 to little ot, and state at time t, little t taking a value little s, then that alpha t of S is equal to something, should have written Q here, but let's say E. E is just in the state little s, what's the probability of observing little ot? Okay. So that's the emission probability. That's why E is being used here. E stands for emission. The emission probability times an averaging over S primes. Okay, all the S primes are all again the state values from which you can reach state S. Okay, all the state values from which you can reach state little s, and the alpha t minus 1 from that state S prime. Okay, so what I'm trying to say is that a bunch of alpha t minus 1 S prime, so bunch of alpha t minus 1 can be used to just compute the next alpha t. So alpha t of s has a longer, O1 to OT and st. Alpha t minus 1 of s prime will be something like O1 to OT minus 1 and some s prime. Okay, so a little bit smaller term. Okay. Similarly, alpha t minus 1 itself is again going to have a recursive expression like this, which will be involving alpha t minus 2 term and so on. So you're basically trying to not repeat computation wastefully. Okay, so you're trying to first compute. So the idea here, again, recursion idea, is start with the base case, and then you kind of keep constructing the solutions of the bigger and bigger problem. Okay, so anyway, the punchline for this slide, without all this manipulation, is that alpha t, which is a term that we define. Okay, this is not intuitive. This is not something you can easily come up with if you want to start from scratch with a model similar to HMM. It just happens that people figure this out, that this with alpha t there's a recursive relationship, and with that we can compute alpha t efficiently, alpha t of s efficiently. So what is alpha t of s? How is it useful for my original question? We're going to relate it in a couple of seconds. Let me also briefly mention that again, whatever you're seeing in this slide, or the answer to the question which I said is it's called forward algorithm, as well as the Viterbi algorithm, which is the answer to the most likely sequence of states. They've been given names only because they were invented in different subfields. There is now a general, more general approach to address solving these types of inference problems. Okay, solving these types of inference problems is a little bit more general approach. One of a popular approach. It's called belief propagation. You might not have heard about it. It used to be there as a part of IDS 576, but anyway, so it's basically a way to mechanically manipulate terms such that you can efficiently compute answers to questions like this. Okay, conditional probability of some random variable given other random variables, and most likely sequence of a bunch of random variables given other random variables, and so on. That's belief propagation. Special versions, forward algorithm and Viterbi algorithm, are what we're seeing today. Okay. Okay. So this is recursion, and so let's say if the recursion in the previous slide was correct. Okay, we didn't check all the equations, but let's say it was correct. Then how we can actually solve for okay, we can solve for the original question, the first question. The first question was, what is the likelihood of a given sequence of observations, right? If you see alpha t of s, it has a probability of observed collection of terms up to time little t and an extra state. Okay, so what if we did alpha capital T of s? If we can do alpha capital T of s, then we will have the probability of the full observation O1 to O capital T, and also S capital T as well. Okay, now we have an extra term. We can actually marginalize out, average out with an extra term, and then we'll actually get the probability of the observed sequence. Right. So now what did we do in the previous three slides is just a way to compute this intermediate quantity in a recursive way. And once we can compute the recursive quantity, we can compute it all the way to alpha capital T, and then average out the ST to get the probability of the observed sequence. Okay, this is the likelihood of the observation. This is actually the first question. Okay, the first question, not the second question, but first question. We'll talk about the second question in the next couple of slides. Any questions here? Is everybody lost at this point? I'm not trying to dwell too much about the details of these expressions here. I'm trying to connect at the higher level of how it's related. Okay? We just need to find the recursion. For HMM, somebody found the recursion, and with that we can answer the first question: the likelihood of the observed sequence. Next, we'll try to answer the most likely state given the observed sequence so far. Okay, that is the second question in that slide. I think going through this example, it's a nice worked out example, but going through the example is gonna tire you guys out, so I will skip that. Yeah, it's just showing how to compute alpha 1s, and then alpha 2s, 3s, sorry, 2s, threes, and so on. So it's animated, but basically, ultimately, you get some alphas, final alphas, and then you sum them up. That's a like probability of observed sequence. Okay. Now let's talk about the second question. Okay. Second question was about, hey, you're observing something. Observation 1, observation 2, observation 3, observation capital T. Tell me what's the state value. Okay, what's the state value? What is the hidden state value? Remember, hidden states are never observed. You are just hypothesizing that there are these little n number of states. So you want to say, hey, what is the likely state value given your observations so far? Right? So for that, we're gonna create another recursion. Okay, again, ignore the intermediate equalities. The recursion involves a parameter or a term called beta of t of s, and this beta of t of s is actually looking forward. Okay, very similar to alpha. Alpha is looking O1 to little ot. Okay, here it's ot plus 1 to capital ot plus 1 to O capital T. Okay, and also it's not a joint. It's not a joint. It's a conditional probability. The conditional probability of these observations given the state at st. Given the state at time t is little less. Okay. So it's some arbitrary choice here. Just at this point, it's like there is no intuition for why this is the right term here. But if you define beta t of s to be something like this, okay, this is a forward-looking term. The probability of a forward observation given the current state, given the state at time t is equal to little less. Then again, there is an recursive relation between beta t of s and beta t plus 1 of s. Okay, so beta t of s involves more terms. Okay, ot plus 1 to capital ot, O capital T. That beta t is related to some sort of summation over next state. So you're going from little s to little s prime. There's some transition for probability value, that number, times emission probability value of, hey, at s prime, if I want to emit ot plus 1, there is some probability value, that's the second term, times all the times beta t plus 1 of s prime. Okay, so if there are n s primes, little n s primes, then there will be a little n number of such terms, and so what I'm trying to say is that there are n beta t plus 1, which all together help you determine beta t, okay, at time t. So at time t, beta can be determined by if you have already computed t plus 1 beta, and they are smaller problems. Okay. So again, given that, why is it useful? It's useful not at this point, which is, of course, you can just do recurse, which was shown in the previous slide. Beta t of s is related to beta t of s t plus 1 of s prime. But if you can compute this beta t of s like this in a recursive manner, you're saving computation. Okay, so all the discussion we are having, by the way, inference problems, the 3 inference problems we are seeing, it's all about computation, how to efficiently infer. Okay. So we can, once we have the recursion, we can actually do. Okay, I'll skip the computed numbers here. You start with the last column and compute up to first column. Okay. Once you have that, you can actually solve for the second question. Maybe earlier I mentioned something incorrectly. So the first question that you saw, which is the likelihood of a sequence of observations, it's called the forward problem. The second question that you saw was the likelihood of a specific hidden state given the observation so far. It's called it can be addressed using the forward-backward algorithm. Okay, and the last one, which is the likely hidden state, that's addressed using the Viterbi algorithm. So there's a question, there's the answering approaches, there's a forward approach, forward-backward approach, and then the Viterbi approach. But you don't need to know these names. Okay, at the end of the day, you just want to compute some conditional probabilities. You can compute these conditional probabilities if you know a handle on how to use recursion, basically. So how do you compute the likelihood of a hidden state given the observation so far? So what is the probability of not just the final hidden state, but any hidden state? Probability of st is equal to s given all the observations I've seen so far. Okay, O1 to OT. Then what you do is you compute alpha t's and beta t's according to the recursive equation, so that it's efficient. Okay. Once you do that, then for any state and any time, so if you want to say, hey, what is the probability that at some time, at some time little t, the state value was little less, what is the probability of that? That can be computed very simply using this equation here. Okay, so this probability of ST is equal to little less given the observation. It just, again, a bunch of, a little bit of use of the assumptions that we made. Just going to be equal to alpha T of S times beta T of S divided by a sum over alpha capital T of S. Okay, so so this is how you would have you would have this value. And so given this value, you can say, hey, what is the most likely state at any given point of time given this observation that I've seen so far? Okay, so the most likely state is going to be the argmax of this. Pick every state, compute this value, whichever state gives me the highest probability, conditional probability, that's the value, that's the likely state, right? That's argmax of this thing, this expression here. That argmax, again, you can see that argmax is just this term here, and actually we can drop the denominator. Why can we drop the denominator? Because the denominator doesn't have anything to do with S. Okay, it's something to do with S prime. It just, in fact, S prime is an internal, I guess, summing variable. So denominator is some constant. Okay, it doesn't depend on S, and that's why you can just pick the product like this. So if somebody asks, what is the like if you can compute alphas and betas, and then somebody asks what is the state, what is the likely state at any given point of time, you can just take at that state, if you can compute alphas and betas, you can just multiply them and take the argmax. Okay, that's the likely state at a given point of time. Now let's look at the last question. This is going to be the, I guess, the end of this lot of equations that you're seeing in the slide. But we're not going through the equations. Again, I'm trying to say, let's keep at the high level and understand what the question is. So original question was, what is the likely state given the observation? Okay, so likely state in the sense that if you see observations little o1 to little ot, hey, tell me what all corresponding hidden states could, what is the most likely hidden state sequence that happens, transpires. Okay, we don't observe them, but what is the most likely one? Okay. So for that, you can use the alpha betas from before. Okay, for that, let's define another variable, okay, intermediate quantity called delta T of S, which again, looks like a max over a bunch of states, probability of a joint probability of the states, fixing the current state value to be some little less, and the observation so far. Okay, so some again non-intuitive definition, non-intuitive quantity that you can define at a given time at a given state. Okay, given time, given state is fixed. Everything before that and everything after that. After that, of course, there's sorry, not everything after that, but these observations are fixed. Okay, they're not, we don't change them. The previous everything before that, all the state values before that, we don't know, so we can take a max over them. We don't know what they are of this term. Okay, so we can't solve it, but let's define it this way: delta T of S. This term also has a recursive equation, which is written here. So it's a delta T of S prime times the transition probability of S prime to S times the emission of OT plus 1 given S. Okay, some expression like that. So if you have, this delta T has a recursive equation. Okay, that's the punchline of this slide. It's not important how, what the manipulation was, but we got a recursive equation for delta T. Then what we can do to answer the original question, which was what the most likely sequence, is we can answer it via maximizing delta of capital T of S. Okay, maximizing over these S's. Okay, so yeah, so I don't know if it's useful to talk about intuition. So we start with some base case, so delta 1 of S to be some value, and we keep track of what is the likely state. Currently, likely state is 0. So remember, states take values 1 to n, 1 to little n. What we're gonna do is try to figure out recursively from delta 1. We'll try to get to delta 2 to delta 3, and so on. And while doing so, we'll also take not just each delta has a max term in the front. So if there's a maximization, there's going to be an argument that maximizes that. That argument, we're just storing it in an auxiliary variable called v subscript t. Okay. That argument itself is going to be our solution. So the argument, so v subscript t of little less, whatever the value takes, is going to be our state value, and maximum maximization over S of delta T of S explicitly gives us is exactly equal to the maximization of our state values given the joint distribution between the states and the observation. So our original problem, what is the likely state given observations, is exactly this problem. Okay? So if you have a joint distribution O sub x, tell me what is the sequence of states that maximizes the joint distribution. That's the problem here, and that's exactly equal to max over S of delta T of S, and so I can compute delta T recursively. Okay, so to compute the most likely state is also achievable via direct programming. Let me so there are a lot of equations here. Let me come back to the question so that in case the questions are remembered. So as I said, the departure is it's not a supervised learning problem. The questions being asked are different. Okay, that's first thing. And so if you had the model already, if somebody told you, hey, here's the pi, here's the parameters for the transition, here are the parameters for the emission probabilities, here are the parameters for the starting state, then these are examples, popular examples of questions that can be asked. Okay, the first question is what is the probability of the sequence that I observed? Observe something, maybe the stock market prices or the collection of words. What is the probability of that observation? Okay, under my model, because model already has the probability, so parameters. So you can tell me what is the probability of this observation. That one you can solve using forward algorithm or the alpha parameters, recursion related with them. The second one is about what is the likely state, any state or the final state given the observation so far. Okay. So this question can be answered using the forward backward approach, basically this condition probability. And the last one is asking, hey, what is the likelihood of so what is the most likely sequence of states, hidden states, given the observations that are observed? Okay. Either you can, whether you do a conditioning or you put a comma here, it's the same, by the way. But basically, you observed a particular sequence of observations. Tell me what's the likely state behind it. Okay. What is the likely state values behind these observations? Okay. That's the question that can be answered using the delta stuff that we saw, recursion delta. Okay. So the only thing remaining now is how do you learn these parameters? Okay? And that is also involved, and so we'll not really talk about them very too much here, except for one quick point. Let me go there. What are the parameters? I'll just mention that, and I'll say that this is not correct here at the bottom. I mean, it's correct with a caveat. Okay? So what are the parameters, right? Let's just talk about learning for a second. Learning the parameters of this model. Remember, we need to have a distribution over the state, an initial state, or at least the starting point of this Markov process. Okay, this hidden Markov process. So that distribution, since the number of state values is n, it will be n minus 1 parameters, because if you know n minus 1, they have to sum to 1, so the last one can be inferred, right? So n minus 1 parameters here. Transition probability, remember, it's an n cross n matrix, so but row sum is equal to 1, so that's why it's n times n minus 1 parameters. Similarly, observations given states is also another parameter here, emission matrix. Q or E would be the notation here, and that's n times m parameters, but m, each row again has a sum to 1, so that's why it's n times m minus 1 parameters. So these are all parameters that you need to learn given a bunch of observation sequences. So very similar to supervised learning, think of each observation, each example to be a sequence of O1, little o1 to little ot. Okay, maybe the same length, maybe different length. Okay, so and there is no label. So you have basically short sequences, a bunch of short sequences or short or long sequences. Okay, like bunch of sentences. Okay, each one is an observation, and given the observation, you are going to translate that to these many numbers. These many numbers, if you have those many state values and those many observation values. So for the natural language example case or the sentence case, m is the number of words. Okay, number of emission. You're emitting a word, so number of words. Little m is going to be the vocabulary size. What's going to be little n? Little n is going to be, if you're doing part of speech tagging, it's going to be the number of parts of speech. Okay? If you want to assume like that, the little n can be something you choose. Okay, a priori, sometimes in some applications you don't know how many hidden states is there. You choose different hidden state numbers. You don't even know how to interpret them, but you'll have to post hoc interpret them as, hey, this hidden state probably means some state of the individual or some state of the market or something like that. The parameters are easy to estimate if you observe both the observed sequence and the hidden state values. If you know the hidden state values and the observed sequence, like pairs of things, then the problem can be solved using MLE. Okay, and that's just a counting and normalizing, very similar to Naive technique or Gaussian discriminant analysis. Okay, just count by count. But the problem is this doesn't work if you don't know, what the state values are, because that is something you have not observed, right? So then you have to use an EM-based algorithm called Baum-Welch algorithm. Yeah, to summarize, I mean, it was kind of dense over the past 30 minutes or so. But to summarize, HMM's formalized sequential observations of a dynamic system. Okay. So in particular, you don't have to do hidden Markov modeling unless you have this aspect of, hey, something I'm missing, and that's what's driving the observations. Okay, that's what's kind of important here. And so we are assuming that each state is hidden and its observation is not necessarily fixed, as in like it's a random observation at every state. Okay. Inference and decoding. Inference, okay, let's not worry about decoding here, but inference can be solved efficiently using a dynamic programming approach, which for us, at least for this context, is just recursion. Okay. Forward vector algorithm for some two of these questions there with alphas and beta recursive terms, and Viterbi algorithm for finding the most likely state. Okay. And parameter learning can be done by MLE is not correct here unless you observe the hidden states as well. So please, so remember that this is not correct here unless you observe the hidden state sequences. And it can be used for time series analysis in many different applications that we saw: DNA sequencing, market analysis, stock market analysis, or natural language processing and things like that. Any questions here? Okay. Okay, let's take a 9-minute break and then we'll switch over to k-means. We'll switch over to k-means, yeah. Okay, let's resume. So what I'm going to do is like not immediately switch over to k-means, which is the subject for the next 40 minutes or so. But before that, I want to give a couple of hints, or basically at least the logistics. So if you look at assignment number 5, question 2 is hidden Markov models. Actually, very small example 3. 2 state values and basically 3 states, 3 state realizations, or 3 time indices basically. So based on our discussion so far, you should be able to answer this question. So the challenging part is going to be k-means is also fine. We're going to cover k-means right now in the next 40 minutes. The challenging part is going to be principal component analysis. Okay? It's something I don't want to rush into today. Especially if there's no time. But for the scope of this assignment, it turns out that you don't really need much of background in PCA, except certainly how to read scikit-learn's documentation and apply PCA. Okay. So I think there's a huge list of examples here, but you should be able to see what PCA does. It's basically a dimensional reduction technique. You might have seen it in other course. If not, totally fine. You should be able to see the examples below to get a sense of what does it do. It's basically applying what is called singular value decomposition on the input data matrix, okay, and reducing the dimensionality. Okay, so if you have an input vector of length 5, so you have 10 of those, instead of those 10 5-length vectors, you'll have 10 2-length vectors, or 1-length vector, which is probably enough. So you'll have to call this function. Basically, you don't have to write you can certainly call numpy dot you know, .linarg.svd or whatever. So you can do that, but you can also, you know, use .pca as well. It's totally fine. Okay. So in the question, you actually just have to create a synthetic data set before. So a synthetic data set and apply PCA such that some nice property holds. That's first part. Okay. And once you do that, then you can just run k-means on the original data, k-means on the PCA version of the data, and then just, you know, compare and contrast. So it's really about k-means, but it's just that PCA is being introduced as a pre-processing step, and just understanding whether how do PC and then k-means is different from just doing k-means directly. Okay? That's the idea. So you can, I think there was a question in the chat as well. So you can use the scikit-learn, you know, PCA subroutine to do that. Actually, there are a bunch of examples at the bottom that you can see. I mean, including a demo of k-means also, but basically PCA on the iris data sets that you might have used in other assignments, for example. And in fact, there's a PCA example here itself, and few other things. Okay, so I would suggest having a look at it. We don't have time right now to look at all this. Yeah, so for example, here you're basically fitting a plane in a three-dimensional data set. So 3 dimensions, 2 dimensions, for example. You're saying although the data is 3 dimensions, 2 dimensions are actually the only ones which matter, for example. Okay. I will skip these. Yeah. Let me skip all this. Okay, so that's about the assignment. Any questions? If facing any difficulty with the previous questions? So in terms of the questions themselves, they were PC and k-means. K-means is what we're going to cover right now. HMM and then Navy-based models. Okay, so that's the collection of questions here. So from the last lecture, this lecture, hopefully, and PC is one extra thing, which is, as I said, you just call the function here. Okay. If not, I'll highly encourage you to look at Hidden Markov Models Wikipedia page. For example, here the application list. Some of them we mentioned, part of speech tagging, DNA sequencing, I guess, gene prediction, and so on. So there are problems where HMMs kind of may be a good starting tool, may not be the only tool. There are other ways to approach the problems themselves, but a good starting tool. And here you can see the types of problems that you can address. Okay, so in the section called inference, we looked at 3 questions. One of them was probability of an observed sequence. That's one question here that's being mentioned here. The other 2 questions are related to, you know, what's the probability of the hidden state given the observation so far, you know, which is basically what's the probability of the last state, you know, most recent state xt given the observation so far. That's called filtering. Okay. Or if you ask what is the probability of some previous state given all the observations, you know, previous state or any, you know, any state, for example, that's called smoothing. Okay, so they're just names. Don't worry about the names. At the end of the day, all they're asking is, I mean, if you have the model, all you're asking is, hey, what's the conditional probability of something like this? What's the conditional probability of something like this? Okay, so these 2 conditional probabilities again can be computed using recursion. The last one is the example that we saw. Most likely explanation is what's the most likely hidden state that gave rise to certain data set, right? So that's, for example, what is the most likely part of speech tag that explain a particular sentence. Okay, so part of speech tagging can, if the HMM model structure is correct, then you will get the parts of speech for any sentence. Okay, of course, HMM model makes certain conditional independence assumptions which may not be correct, but if it is correct, then this is the way to get part of speech tags, for example. Okay. But in general, I think I strongly suggest looking at this because it's a very basic model, applies to a bunch of fields. So it's good to understand this one, just like linear regression or something else, to get a feel for this type of a model. Of course, in each application, there may be a better model with its own assumptions or its own variation. Okay. Any other question on chat? Yeah, so there's a question which is about Laplace smoothing. If one version is better than the other, we only saw one version per model, so it's not like we have multiple choices per model. As I said, you know, the smoothing parameters themselves, 1 divided by 2 or like 1 divided by vocabulary size, you can actually change them as long as you are consistent with the, so the sum equals to 1, for example, the sum of the conditional probability is equal to 1, right? So you can change them as you need. Okay, they basically, if you have a Bayesian perspective, they are supposed to be just priors. Okay, they are just priors which kind of influence the posterior distribution. So you have, if you have prior that the probability of a word is not 0, but your likelihood, if you just focus on likelihood model, it's saying 0 by 0 or something. Instead of that, if you want something else, you can use the prior. Okay? That's what it is. Okay, with that, let me get back to the slides. So the scope for now is basically just think of k-means. I think k-means, have you guys seen k-means before? You have. Okay, so this part should be easy, or at least a recap. So let me see if I'm sharing the screen. I am, right? All right, nobody complains, so I assume I'm sharing the screen. Okay, so what we're going, shifting gears again a little bit. So we kind of spent some time on generative models up to before the break. Now we're gonna shift gears and talk about just unsupervised learning. Okay? So supervised learning for a lot of lectures, then a little bit of generative models, but still supervised for till at least naive and Gaussian discriminant analysis. Then hidden Markov model is really unsupervised. It's already an example of unsupervised as well as generative. Now we're going to look at non-generative unsupervised learning methods. Okay? So the thing is, they're not very big distinctions. So each one is having some tag or the other. But let's look at k-means as an example of an unsupervised method without a generative interpretation. Supervised learning, it's all about fitting a relationship between input and output variables. And you can fit, underfit, and overfit. And there's some fit choice that we can do using model assessment, model selection. We spent a lot of time on that. So unsupervised learning is about no labels, right? So here we had A, B, and C as labels. And unsupervised learning is all about, again, just some data, very similar to HMM. So there's some sequences, or in this case, some data points. And we want to learn patterns related to these data points, right? So generally the patterns are, set patterns. Okay, these data points belong to one set, the other set of other bunch of data points belong to another set, and so on. Okay. Hard, here the bracket, there's a, I guess a word called hard. That just means when we kind of ascribe these patterns, hey, these bunch of points belong to one set, we want to say that each point can only belong to one set, for example. Okay. If we want to impose that, that's called, it's basically, that's what hard means here. Or you could have, a software version where a point could have like a mixture, like it could be part of multiple sets. Okay, so it's not well drawn here, but basically, you could have a soft version of, hey, the point can be, part of one set or the other. Then you can have a mix like this. Okay? Or actually, let me just step back. Hard just means you have exact. So if you knew the colors, okay, which is not the case in unsupervised learning. If you knew the colors, then you just want to ensure that reds are in one side, the greens are in one side, and so on. Which we don't know, we don't have. So sometimes you can have a situation where a set may have points from which are actually supposed to be from different sets originally. So anyway, this distinction is not super important. What I'm saying is you have a bunch of points without labels or without supervised signals, and you want to learn patterns of it and display patterns from them or some summarization of them, generally sets. Okay, and that sets are basically clusters. So I guess what can we do with data without labels? Basically, learn the probability of X. Basically, that's what we do when we say patterns. X is what the input is, right? And it can actually help prediction, but we'll talk about prediction later. We'll focus on unsupervised learning for now. Once you do unsupervised learning, certainly can feed into downstream analysis, downstream prediction problems. But for example, you can do unsupervised learning first, do some clusters, and then once you get the clusters, per cluster you can build a regression model. Or per cluster you can build a classification model. Okay? That's totally fine. So here's an outline. We'll actually try to look at a few topics next time. Today we'll focus on k-means, keep it slow, look at k-means today. And then next time we'll try to touch principal component analysis and mixture of Gaussians, and maybe expectation, not unmaximization, expectation maximization as an approach. So maybe we'll not get time to do independent component analysis. We'll see. Okay, so that's for later. But these are all examples, except for the fourth bullet point, examples of approaches, analysis techniques. Okay, and we'll start with k-means clustering as a starting point. Okay. Unsupervised again just means no training, no supervised signal, annotated data. It's just trying to do exploratory analysis on existing data, and so there is no benchmark of success. Okay, there is no objective benchmark. There is no accuracy. There is no ROC curves. There is no F1 scores or precisions and recalls. Nothing like that. Okay. Okay. So before looking at clustering, k-means as an algorithm for doing clustering, there are many other unsupervised learning problems. Okay, so unsupervised learning is, as I said, learning something from data, generally sets. That was the example I showed earlier. But that's not the only thing that you can do. There are many other things you can do. In fact, one of the things that you might have done in 572 is association rules, or basically frequent item sets. Okay? Frequent item sets are also unsupervised learning technique. Okay? Similarly, density estimation is an unsupervised learning technique in the sense that there is no need for supervised learning. There is no supervised signal needed. Okay? Similarly, here there's some named image segmentation when you want to segment roads versus non-roads, or people versus not people. Representation learning, which is basically each word, for example, or each symbol can have a numeric representation. You can learn the representations without supervised signal, or without supervised data, without an x, y type of a data. Okay. Community detection is a problem in social network analysis. So if you have a network, you want to detect communities, it has close relationship to clustering, but it's not exactly a clustering problem. Okay. Similarly, there are other problems, dictionary learning and so on. There are many names to different types of problems, but many of them actually not exactly supervised learning, and they don't need supervised signal. I mean, including HMMs. HMMs don't need a supervised signal. Okay. But because they're all trying to extract patterns, of course, there's going to be an overlap relationship between clustering and, for example, community detection, for example. There's going to be close relationships between them. But let's focus on clustering. So clustering is here's an example for clustering. So clustering phases, right? So first, generally, if you think of clustering, you can just scikit-learn, for example, if you do clustering, the data set is already given. In fact, assignment question number 4, we are generating a synthetic data set, all numeric already. Here is an example where you need to extract frames, you need to extract faces, then you extract features, and based on the features, you do clustering eventually based on the k-means. Okay, so there is a bunch of steps that may be needed depending on the application. So it's not always ready to immediate, ready for immediate use inputs. Okay? So inputs may need to be pre-processed. So here's phase clustering from some data set, I think from a research paper, perhaps. So here's the community detection problem. So here's a social network graph, let's say, with people talking to each other, and there's some links and edges, so some links / edges between nodes or groups of people, and then based on that, you can bucket them into, hey, these are working professionals, these are students, these are white collar workers, and so on. So there are different communities that can be detected, and it's all unsupervised. Can be unsupervised. Of course, you can go out and get annotated data, and then you can do better than probably unsupervised learning. But if you don't want annotations, or you cannot get annotations, and you want to do some exploration with data, then there's a bunch of tools to use. Okay. So if you have two-dimensional data, here it's kind of obvious with the coloring that there are 3 clusters here, or 3 sets of points. Okay, 2D points. Right, but sometimes it may not be, may not be easy. But here is an example where clearly this bird is not the same as the other 3 birds, but it can be hard. Okay, so it can be hard in general, especially because there is no supervised signal. So you choose a bunch of methods, and you have one data set typically in a setting. That method may give you completely wrong results, at least in hindsight. If you think of what is right and what is wrong, it's all subjective. But for example, rows represent different data sets. Okay, different I guess very canonical data sets. Like here's a bunch of 2 concentric rings. here is the two moon-shaped data points. Here's 3 clusters, and here's 3 Gaussian type of clusters, and so on. So here you can see that different unsupervised learning approaches, okay, which are columns here, are doing very differently. For example, here, something called agglomerative clustering is able to get the blues separately from oranges, and this seems intuitively correct, okay, of saying, hey, these inner circle is blue and the outer circle is orange. Maybe not. Maybe it is the case that you need to get, hey, the bottom, bottom left should be oranges, and the top right should be blues. That may also be the case. Right? So with this half moon, maybe this clustering approach is actually getting blues and oranges compared to maybe this technique, which is there are some oranges here and some blues here. Okay, so it's a priori unclear. Maybe in hindsight, maybe with some bias, you can say that, hey, this clustering is better than that one, but it is tricky. And this is for just 2-dimensional data set. Can imagine if you have 10 dimensions or 100 dimensions and you're doing clustering, it's very, very hard to kind of quantify or be sure about what you're doing. Of course, you can derive some partial insights from them, and maybe they are enough for you to make actions or downstream decisions. Okay, so with that, brief background, let's talk about k-means clustering. Since some of you have already seen this, hopefully you can correct me if I'm saying, something not correct. So what is the approach? Okay, so now we're directly jumping into approaches. So the problem is to cluster a bunch of points. So each point we want to assign a label. Hey, this point belongs to cluster 1, this point belongs to cluster 2, this point belongs to cluster 1, and so on. Okay, so bunch of points, you just want a label for them. Okay. So what we have is a data set. Now y's are missing. X1 to xm are the points. So m points. And we also, let's say for simplicity, also give you the number of clusters. Okay, so I want to choose 5 clusters or 10 clusters. Okay, the choice of the number of clusters is also something you need to figure out what is the right choice, especially and it may be not trivial. Sometimes it's easy. But let's say we've been given k and these points. Okay. So given that there are many approaches to solve give this cluster labels. One of them is k-means. And so how does k-means work, right? So it works in it starts with some initialization and does something and then does something very in a recursive way, not recursive, sorry, in an iterative way. Okay. So what does it do? It starts with some initial. So we assume that all these points belong to an n-dimensional vector space. So x1 to xm, all these data points are in n dimensions, little n dimensions. Okay, just numeric. So it's not really categorical here. Once you have these numeric vectors, then you start with some k points in this vector space. Okay? So some k points, mu1 to mu k, some arbitrary so some arbitrary points mu1 to mu k. So these are just randomly generated vectors again in Rn. You can also use some random, some arbitrary k of the original data points also as initial centroids if you want. Okay. These are called centroids, and we'll see why they are called centroids in a second. So you start with some initial cluster centroids. Okay, so the intuition is that these are kind of points. This eventually should be lying as the centroid of each cluster. Okay, of each set. Initially, we don't know where the clusters are, so we just start with some running points. But what we want is that we want to get these centroids to hopefully the appropriate k number of clusters, and the centroids live in those clusters. Okay. So what do we do? There are 2 steps. In fact, there's some connection to EM, the expectation maximization approach I was talking about for generative models or graphical models. But we'll do the connection next time. But what is the approach? It's an iterative approach. It's an alternating optimization approach or alternating minimization approach. So what do? We do 2 things. In step 1, given the current centroid, we assign cluster labels to each point. Okay. So for each point, the little m number of points, we assign a cluster label. So we just say, hey, this point, which of the k centroids is it closest to? If it's closest to the third one, so my cluster label for this guy is number 3. And if the second point, which of the k centroids is it closest to in terms of the Euclidean distance? Okay, this is again a specific choice being made by this approach. If maybe the fifth centroid is close to it, then the cluster label is 5. Okay, so you get a bunch of numbers. These numbers should be between 0 to k for each, 1 to k for each of the points, each of the data points. You assign a number between 1 to k. Once you have these, then now what you're trying to do is update the centroids themselves. Okay, so now I have a candidate cluster labels for each of the points. I could say, hey, I already have it, but I already have the clusters, but that's not correct. And the whole point is to alternatively optimize for the cluster centroids and the cluster labels. So now we have the cluster labels. Now what we're going to do is optimize for the cluster centroids. Okay, so how do we optimize the cluster centroids? There's actually a least squares problem here as well, but it just boils down to doing, hey, if these 10 points belong to cluster 3, then the average of those 10 points is my cluster center, okay, or the new cluster candidate. So for the case cluster, just look at all the points that have been assigned to the case cluster, just the average of them. Okay, so in fact, unweighted, like uniform average here, just an average of those points. Okay, so that's the new cluster center for each of the capital K number of clusters. Okay? And you keep repeating this until something called convergence. And we've seen this convergence idea briefly when you did the gradient descent, right? So convergence just means, hey, here in the iterative process, either I can do a for loop with a max number of steps, or I can do a while loop where I check for some condition to hold, right? So basically here we are at least in the pseudocode we're saying, let's do a while loop where we check for some condition to hold. And that condition is basically, maybe the cluster labels don't change from iteration to iteration, or maybe the cluster centers don't change too much from iteration to iteration. And the too much is exactly like, they take the norm of np.vinal.norm, for example, the 2 norm between vector previous cluster center and the next cluster center, if the difference is very, very small, then you say, hey, the cluster centers are not changing, so let's just stop. Okay. So here's an example. With we're trying to get 3 clusters, so 3 colors here, so blue, red, and purple. And what you do is, given the initial cluster, so here the initial centroids happen to be the same data point. Okay, some 3 data points in this data set. Okay, so we did the initialization. Next, we need to do cluster assignment, right? So we look at what are the closest points to red, closest points to purple, closest points to blue. So we see these are all the points, and so we've now given the cluster labels. Next, given the cluster labels, now we want to update the cluster center. So you can imagine for these blue points, the cluster center will be somewhere here. For these 2 red points, cluster center will be somewhere in between. And given these purple points, somewhere in the center, right? So that's what happened here. And now we have new cluster centers. Now we want to get again new cluster labels, right? So now you can see which clusters. So you can see that the blue point is very far away from blue, but it's somewhat close to red. So this blue point can, for example, get converted to red cluster label. So that's what happened here. And maybe you again update the cluster centers themselves. They slightly move, and the average of these 3, the average of these 4, the average of these 5, and then they stop moving, and maybe then you stop. Okay, that's where convergence happens. Okay. Actually, no. Here, even that point also got converted to red. But anyway, so that's yeah. So I guess yeah, this is where you kind of stop. Any questions about this k-means algorithmic approach and the illustration here? We'll briefly talk about the objective function, because there's always there's an optimization problem. There's an objective function. I will briefly mention that now. Before that, I want to kind of check if there's a question about this. If there's any question, no?
We got the categorical variable.
Yeah. So k-means is making a specific assumption about being in the Euclidean space. There is a closely related approach. So first of all, if you don't want to worry about whether the original vectors are categorical or not, you can decouple the problem by just focusing on k-mediated approach so that its input is not the data points themselves, but actually the similarity matrix. Okay. But how do you compute similarity when you have categorical variables? This is actually comes back to the first lecture. Somebody gives some distance measure. So you can have different distance measures for categorical variables. Okay. I mean, I don't know, you are in deep learning, I believe. So you can actually, for category variables, you can do embedding. And so now you have vectors. And so you can also find distances, right? But otherwise, one-hot encoding and stuff. But the problem is they don't So if you want to encode a category variable, there is no notion of a distance between category 1 versus category 2 and category 3 versus category 4. They're all equidistant from each other. So I don't know how much that kind of influences or makes this problem messier. Okay. Yeah, I guess that's no. I went on a tangent there, but basically category variables we are not discussing right now, unless you want to do it one-hot encoding and then you have a longer vector, and it's a vector in a vector space, and so you can still think of Euclidean distance as a reasonable choice. It may not be. Once you do one-hot encoding, Euclidean distance is not a good choice. Okay, so actually, in fact, here's the question. So, what distance we use for evaluating distance to each cluster center? We use Euclidean distance, right? So we did the two norm square or two norm between each data point and the current candidate cluster center to assign that point to a cluster label, right? The assignment was hard assignment in the sense that each point at any given iteration step is being assigned exactly one color or one cluster label. Okay, but you can imagine, hey, I'm close to 1 point by 3 units, and we close to another cluster center by 4 units. Maybe this point should be 3 out of 7 times related to one cluster and 4 out of 7 times related to another cluster. You can do some assignment with the stop. Okay, so a point can be part of 2 clusters, right? Well, that's not the case for k-means. Okay, so we'll briefly talk about a, I guess, a slightly different application example here. So if you have, let's say you have documents, and then you can create a bag-of-words representation, and let's say it's a multinomial version, which just means that bag-of-words representation means you have a vector which is the size of a vocabulary, and multinomial just means that you're just counting the words instead of just looking at presence and absence of a word. So some coordinates could have counts going up to whatever the number of times the word appears, and so you can ask like what document is closest to a given document Q. So each document is now represented as a vector in in the vocabulary size vector space. And exactly what he asked. So can we use Euclidean distance or should we do something else? Here we briefly going to mention a different approach. In fact, cosine similarity, but to break the suspense there. But basically, how do you say two vectors are similar when Euclidean distances may not be the single best choice? So here is slightly it's a different choice. Okay, and I'm not saying that one choice is always better than the other, but cosine similarity makes sense for this application. Okay? Makes more sense than distance. So the cosine distance, okay, so distance and similarity are opposite to each other. So more similar, less distance, okay, or closer, okay, smaller distance value. You want to have that. So that's why let's say you have two vectors x comma z, then you want to say distance between x comma y is related to similarity in some way, inversely related. And so here's a very simple example where it's just 1 minus similarity as long as similarity is bounded between 0 to 1. Okay? If similarity is bounded between 0 to 1, this is a perfectly valid choice. You can do other things, e to the power minus similarity, for example. Okay? So what do we do with x and z? So instead of computing Euclidean distance, we are actually doing something else, which is this function sim of between two vectors is just the inner product between those vectors scaled by their magnitude or scaled by their norm. Okay? So it's just similarity of x comma z is x transpose z divided by the norm of x and norm of z. Okay? And what are these? If you just really expand out with respect to their coordinate wise indices, then it's just the sum, element wise product and sum, and then sum of squares, sum of squares. Okay, so so this is an example of a similarity measure which is different from Euclidean distance, and maybe this is a better way to encode distances between points. Okay, and replace one of the steps, right? So in one of the steps we are using Euclidean distance to assign a cluster label to each data point. Instead of that, maybe you can use cosine similarity, but then it's going to be a different approach. Okay? There's also an assumption in the second step where you're trying to compute the new cluster center that also actually assumes a kind of a Euclidean distance assumption. Although we didn't see that, so it could also pose a problem. But you can do cosine distance between points and have then apply a different algorithm called k-measure. Okay, now let's come back to a brief comment about the k-means. So k-means is doing some optimization. It's doing something iterative, like SGD, right? SGD is doing an optimization of the original objective function, or a batch training descent and so on. So here, k-means is also doing optimization of an objective function. Similar to PCA is also optimizing something. Okay, we'll see PCA next time. Similarly, HMMs, we are optimizing something. Okay, so especially if you're learning, as I said, it's a EM based, some likelihood maximization problem. Similarly, when you fit Gaussian discriminant, you'll maximize likelihood and so on. So every time you have a problem, whether it's supervised or unsupervised, you are kind of directly or indirectly optimizing some objective. Okay. Fit k-means, the objective is actually written like this. It's a function of two variables. One variable is actually a kind of an integer variable. So C is actually collection of C is the length of m data points, and C is basically a vector which each coordinate says which cluster does the point belong to. Okay, so it's like C is a vector with m dimensions because m data points, and each location is just saying which cluster you belong to. And mu is this collection of vectors. Okay, it's a collection of centroid vectors. Okay? So we are both optimizing for the cluster labels and the centroid vectors. Okay? Although at the end of the day we just want cluster labels, we are optimizing for both. Okay, and how do the choice of cluster labels and the centroids relate to this objective function? It's just the sum over each data point. How far is the data point compared to the cluster it has been assigned to? Okay, in terms of Euclidean norm square. So it's just saying, hey, xi, I assigned a value ci to it, maybe cluster 3, cluster 5. What is the vector corresponding to the cluster 3, cluster 5? Some centroid vector, that's mu. So it's just the distance of the point to mu in terms of the Euclidean distance, right? So that's the loss function. Now, if you have this definition of the loss function, now you can talk about, okay, I can just do gradient descent, but except of course you can't do gradient descent easily because C is you want C to be integers, hopefully, like one of the cluster labels, so one of the cluster indices, right? But if you kind of ignore that technicality, you can actually just do gradient descent here. You have been defined a objective function. It's some variables have to be optimized, and in fact, this is not in a nice way that you can do gradient descent actually. But if you can massage it into a form where you can work with gradient descent, you can actually just do gradient descent. Okay. So here, this is the objective that k-means is trying to minimize. Okay. So how is it minimizing? It's just focusing on this joint objective function and then doing what is called alternating minimization. Okay, it's doing alternating minimization. It's a general technique. Whether you have a objective like this, or even if you have the moment you have an objective of two variables, you can always do alternating minimization. Two variables or more. You can hold one variable fixed and optimize the second one, and then given fix the second variable, optimize the first one. Okay, so it's just alternating minimization, or you can do alternating maximization as well, and so on. So what do we do here? Holding the cluster census fixed, we are optimizing for C, and that's basically giving us, and the way we are optimizing for C is not by gradient descent, by just reassigning the cluster centers for each, so clusters for each data point. Okay, and once we have the C fixed, because this assignment procedure gives us a new C, potential new C. Given C fixed, we are updating the mu. Okay, we are minimizing when we update the mu, we are actually minimizing this J function. Okay. So this is what I meant by saying that the second step of the k-means algorithm is actually also minimizing a squared loss. Although the second step is just saying take the average of the points that have been assigned to you. You can see that if I fix C, then to optimize for a mu for a particular cluster, you have to look at hey, pick a point which has the smallest Euclidean distance with all the members with respect to in that cluster. Okay? So which point is the point that is closest to all the points in a given cluster? Is the point which is the average of those points. Okay? And if your objective involves a 2 norm square, if your objective involves some 2 norm to the power 4 or 1 norm, then it's not going to be the average. Okay, so it's going to change. So this is like there's choices we are making which influence the update rules. Okay, so yeah, I guess a couple of comments. This is not a convex function. Convex function again is that the mental picture should be something like a ball. So there has to be local optimize, the global optimize, and then you start from anywhere, do gradient descent of the thing, you kind of get to a collection of points or a single point, which you don't, from which you cannot get further lower. Okay. Or a convex function is also defined by what is called a convex set. I think we saw the notion of a convex hull when we're looking at drop curve. So a convex set is nothing but a set where if you take 2 points and draw a line between them or some, a line between them, the line doesn't go outside the set. Okay. So a convex function is a function whose level sets are convex. Okay? If you chop the function and look at from the top, the sets look like a convex. Okay? But anyway, so this loss function is not convex. Clearly, the C and mu, they don't. I mean, it's not super clear here, but C and mu, they don't give rise to. So you'll have basically a Hilton value type of a loss function if you really draw this out in 2 dimensions or whatever 3 dimensions. Okay. So which means you can't really get to the ground truth cluster centers, even if it's synthetically generated data, and the data has let's say 3 clusters. Depending on the starting point and doing this optimization, this iterative step that we're doing, change cluster centers, change cluster labels, and repeat it again, you may not get to the true cluster centers. Okay, so convergence is not guaranteed. So you may be oscillating, as in like going to some local minima, some other local minima, some other local minima, maybe back to some original local minima, things like that. So there is, at least in theory, this is not a nice problem to work with, but in practice, it converges. It does pretty well, and there are other extensions to it that you might have already seen that kind of take care of edge cases and things like that. But at least the version that we are seeing in the slide deck, it's not, at least in theory, it may not always converge. Okay? Or yeah, it may not converge, or may converge to a bad cluster allocation. So convergence criteria, as I said, there's a while loop. So what do you choose? If you don't want to use a while loop, you can use a for loop, then a fixed number of iterations, like 10,000 iterations, keep doing the alternating steps. Or you wait until the cluster affiliations don't change, so the C vector doesn't change from iteration to iteration. Or your cluster centroids don't change too much. Cluster centroids, remember, are vectors, floating point numbers, so you can't really do equality checking. Don't do that equality checking if things are not integers or booleans. So with floats, you kind of say, hey, absolute value of the norm of the previous vector minus the next vector, the 2 norm square, for example, is smaller than a threshold, something like that. That's how you need to check. Okay. Any questions here? I think I'm going somewhat fast because some of you have seen this. Any questions in the audience in a second? Okay. Okay, so my illustration of this point about convergence, right? So convergence, as well as convergence not being guaranteed to the right location. So let's say you have let's say you chose some initialization of the cluster centroids. Okay, so maybe this was purple here, there's blue here, and then red here. So this was kind of similar to the previous illustration before. So here you may do fine. But what if you have a setting like this? Okay, so you have a data point, bunch of data points. In 2D, you can actually see that, hey, 2 of the data points seem to be bad. But in higher dimensions, you can't really visualize easily unless you project down, and then you still get a sense of whether this cluster is possible or not, but not much, right? So here, if you choose, for example, this center, and this center, then it will give you a result which may not be desirable. Okay, there's no right or wrong answer. As I said, there's no objective measure of success. But maybe you are actually trying to look for this versus this versus this, and these two are actually just outliers, or some wrong inputs, or something where it was wrong. Some coordinate just was -999 or something like that, right? So if you start with these cluster centers, you will not have good convergence, right? So that's the last slide, actually, this one. So this is what was an example to say that depending on starting point influences where you end up, and that's something that you will not see in a convex optimization problem. In a convex optimization problem, irrespective of where you start, as long as you choose reasonable step sizes and so on, you will actually get to the bottom of the ball if you're doing minimization. Whereas for non-convex problems, depending on where you start, you may end up with different local minima. So here the local minima is this is one its own cluster, this is its own cluster, maybe this whole thing is its own cluster. Okay. Any questions here? Okay, so figure out if there's a slide. Okay, so actually we are ahead of time. I don't want to get started with the next step. But what is missing is for your assignment submission next on 11th is PCA. As I said, use the PCA function in the in scikit-learn, and if you are facing trouble, then certainly you can reach out to me or TA, and we can help you with the PCA part. Okay. But PCA is not really a substantial thing in that question. It's mostly to understand the impact of PCA while doing clustering. Okay, so k-means is what you'll primarily be working with. Okay. If there are no questions, then we can break for today. Thank you.